Welcome all. I'm Mehmet Deniz Güneş from İzmir Enstitüsü of Teknoloji. I will make a presentation is entitled Development of Aluminum Honeycomb Cord Carbon Fiber Reinforced Polymer Composites Based Sandwich Structures and Characterization of their fatigue life. It's also a part of my PhD thesis. Here's my outline. I will give a very short information about carbon fiber reinforced composites, and then it follows that sandwich structures and literature review. Then we will finish with experimental procedure and our results. Here's the carbon fiber reinforced composites part. The usage of carbon fiber reinforced composites is highly increased in recent years due to their superior mechanical properties such as low density, high specific strength, their impact resistance, and high fatigue strength. And their main using areas are in aircraft, defense industry, automotive industry, sports goods and building constructions, etc. And the composites are mainly divided in three parts: particle reinforced, fiber reinforced, and structural reinforced. Today we will talk about the sandwich panels, which is the structural composites. And they are using some different applications. Sandwich structures. What is sandwich structures? The typical sandwich structures consist of a core material that can be a foam core or honeycomb cores, and thin outer skins. We call it face material. And face materials can be metal composites or ceramics. They are stiff, strong, and lightweight. Here the main advantages of sandwich composites, as we said, lightweight. Their specific strength is high, and they have high corrosion resistance. But the most important properties of these structures are bending resistance and rigidity. As I said, it has two parts, lightweight core and face sheets. Lightweight core increases first moment of inertia and flexural stress. Flexural strength is this one, actually. Face sheets carry the bending load, and the intermediate layer carries the shear load. Intermediate layers is this adhesive layer between core material and face. Here is the effect of core material. Core materials led to significant increase in the mechanical properties without weight penalty. Here is the single skin. The T and weight is 1 unit, strength is 1 unit, and stiffness is 1 unit. If we increase this core thickness to 2T, the weight is the same, but strength increases to 6 times and the stiffness increases to 12 times. And if we increase this to 4 times the thickness, the weight is the same, but the strength is the 6 times and the stiffness increases to 48 times. This core is a very light material. They are porous media, generally. Here I will show some literature review and some papers about this subject. First, this paper is published in 2014 in the Measurement Journal. Identification and prediction of cyclic fatigue behavior in sandwich panels. And these researchers, they use the carbon fiber reinforced epoxy as a face material, and the Nomex honeycomb is a core material. Nomex is a kind of an aramid. And they bond with an adhesive layer. Here is their results. They make their experiments with displacement controlled, and R is the stress ratio for fatigue. And load type is 3-point bending load, as you see here. They determined the very important thing, the failure mode. They claim that the first failure mode occurs in the intermediate layer, here, between the core and face sheets. And they evaluate the stiffness loss as a function of number of cycles. This is the second paper by Onur Coşkun and Halit Türkmen. Bending fatigue behavior of laminated sandwich beams is published in 2012 in Advanced Materials Research. They use the face materials the same, carbon fiber, reinforced epoxy, and core metal aramid honeycomb. It's similar with the previous one. Their fatigue parameters, and they do their test as displacement controlled. R is the stress ratio is 0.1, and their frequencies change with 7 and 10 hertz. Load types is 4-point bending, and they published only their stiffness loss, actually. This is the initial load displacement curve before fatigue tests. These are the after fatigue tests. You can see the stiffness loss here. The stiffness is the tangent of this linear area. And the last one is actually the closest one of our study, because they use the face material, they use carbon fiber fabric test face material at the orientation of this, and aluminum honeycomb core. It's published in Kompozit Part A, I guess, fatigue analysis of honeycomb composite sandwich behaviors. They used two different specimens. First of the undamaged specimen, and then they applied the fatigue loads on the damaged specimen. It's their fatigue parameters. They choose the high frequency, the 10 hertz, and load types 4-point bending, and R is 0.1 again. And their results for undamaged specimen and also the damaged specimen. This is the important one, is the failure modes. They indicated that the failure caused the debonding in the area around the rupture, this one, for undamaged specimen. And the failure occurred in the cell walls parallel to the length direction due to in-plane traction stresses, you can see here, for damaged specimen. Then I will pass our experimental procedure. First of all, the materials that we use. Carbon fiber reinforced polymer we used as the face material with the orientation of 0-90 and 4 layers. Our matrix is epoxy resin, and reinforcement is unidirectional carbon fiber fabric. And we use aluminum honeycomb core, as you see here, as a core material. Here's our manufacturing process for sandwich panels. First of all, we produced the face sheets with vacuum infusion techniques, carbon fiber reinforced epoxy. Then we bought the honeycomb cores commercially, and we established those by a help of adhesive bonding. After that, we cured it in 60 degrees centigrade for 35 minutes. And we have also a post-curing procedure for this adhesive. And firstly, we done the monotonic flexural test according to ASTM-C 393 standard. Our load type is 3-point bending. This is our test setup also. Test rate is 6 millimeter per minute according to this standard. Span is 150 millimeter. And we obtained the first force displacement curve. For fatigue testing, we searched the literature for fatigue test parameters. As we see here, the load, according to literature, load type is generally used as 3-point bending, and tests are done with load controlled. Stress ratio is chosen as 0.1, and they usually done the test in low frequencies, 2 or 3 hertz. And then this is our fatigue test setup. It should be video here, but okay. Our fatigue test video is here, but I cannot run it. And it's 3-point bending, load controlled. Our stress ratio is 0.1, and our frequencies is 2 hertz. And we have done the test in 4 different stress levels. And our results. First of all, we obtained the F-ultimate for fatigue test. So that we done the flexural test. This is our load displacement curve for flexural test. We observed also failure modes, and we determined the first failure modes for monotonic load is core crash, as you see here. And it occurs in here. Then a linear path follows this with a low tangent. Here is we obtained the interface failure at the edges. As you see here, it occurs due to high shear load. And the last failure mode is the phase failure. And here is the load is increased dramatically, and the failure is here. Then these are our fatigue test results. It's for 80% of ultimate force. First failure mode is change here. We obtained that the interface failure at 1,100 cycle, as you see here. And it occurs in edges. And the second failure mode is core crash, and it's 1800 cycle. Similarly, is for the 70% of F ultimate. First failure mode is interface failure, as you see here at the edges, at 1800 cycle. And second failure mode is core crash, as you see here. When we decrease the stress level, actually the failure modes are changing. For 60% of ultimate force, first of all, we observe the tearing at core in 2100 cycle. But here, the structure is still load-bearing. Therefore, we didn't assume it as a first failure mode. The first failure mode for this stress level is interface failure, but it occurs in middle of the specimen at this time, at 6500 cycle. And then the last failure mode is the core crash still. We didn't wait for the phase failure because it gets a lot of time. It's already failed specimens. And the last of it, for 50%, core and interface failure occurs at the same time at 11,500 cycle. And here is our ascent curve for the test results. Here is our safe area for designers, design engineers. Okay, to conclude, in this study, aluminum honeycomb core, carbon fiber reinforced polymer-based sandwich panels were developed. Flexural properties of sandwich panels were examined. Then the failure modes of sandwich panels under flexural load were determined. First failure mode was observed to be a core crash under monotonic flexural loads. Low cycle fatigue behavior of sandwich panels were characterized under different load levels. And the initial failure mode under cyclic load was observed to be interface failure. And I want to make some acknowledgements. The authors acknowledge the cost gap for their financial support for this project. Also, innovative materials. And I also special thanks to Mehmet Ziyaokur. He's on his military service now, because this project has begun with him. And my lab mate Serkan Kangal and my supervisor Metin Tanoğlu. And thanks for your attention.